Welcome back. During our forays into materials informatics, we have now covered a fairly large volume of material. We have looked into different types of featureization schemes, how to handle with numerical data, how to handle with microstructural data, and then most recently we were looking at how can we properly interpret and interrogate machine learning models in order to gain some physical insights. So in order to undertake this type of activity, we were using a number of tools that have been already developed, namely tools like SHAP or looking at partial dependency plots or ICs, and then we also looked at another approach, namely that of Cosmore, where we used the composition as a stimulus. The main idea being that the features are correlated, and when you change one feature, multiple features will actually change. So that was a basic idea with which we were starting to interrogate this type of models. And then after that, we also showed some examples as to how one can interrogate the models and start understanding how different features contribute towards the performance of the model. Now, there are really two ways of looking at this. So one way is you create this type of a black box like model, and then after you have this black box type of model, you go ahead, run it, interrogate it, and so on and so forth. The second way, which is something which has been gaining traction in the last 5 years or so, is that you ensure that the model you are building in itself is physics informed, and therefore you are almost assured to capture the underlying physics using the machine learning model that you have been making. Now, this field of physics informed machine learning is quite vast, and one can actually make different types of machine learning models physically informed, but we will look at one type of such an approach, which is basically physics informed neural networks. So physics informed neural networks has been in vogue for the last 5 years or so, and in these 5 years one has seen a lot of applications of this type of approach, and therefore instead of looking at all of the physics informed machine learning models, we will simply take up this concept of physics informed neural networks and try and understand this over the course of the next few minutes in this lecture. Now, if you look at your traditional neural networks, there are a certain number of challenges that one has to deal with, and these challenges are even more pronounced when you consider that we are looking at the world of materials. The first thing one should keep in mind when you are using neural networks is that these networks perform the best when there is a large volume of data that is available in order to properly train the model. Now, this is not always feasible, as we have been saying ad infinitum that materials informatics is really more of a sparse data problem. So it is not quite common that you will have a large volume of data always in order to train your model. But at the same time, the neural networks do have some unique advantages, in the sense that if you look at the different activation functions they have got, those activation functions happen to be this nonlinear type of terms, and when you have this nonlinear terms, you can pretty much use those type of functions to fit any data. So this was the first drawback that one faces when looking at this neural network type of models. Even if you were to try and collect a large volume of data, it is not always feasible. So that is again a constraint, mainly from the experimental perspective, whether you think in terms of cost or whether you think in terms of the time requirement. Now, this second part, of course, you can address this, as you will see later on when we talk about techniques of doing very high throughput work by doing some sort of combinatorial material science. This is something that we will be discussing a little bit later in one of the subsequent lectures. But despite all of that, collecting a large volume of data is not always feasible. So what do you do when you want to use a machine learning model that requires a large volume of data, but at the same time getting that large volume of data is not always feasible? So one of the methods that we had discussed, which can mitigate the problem only to some extent, not completely, but only to some extent, is one could work with an ensemble of neural networks and then use averaging techniques in order to get better predictions. But then there can be other approaches. So the other approach that we want to discuss today is, can we actually use the laws of physics in order to generate our data? So when we talk about physical laws, one has to understand that when we talk about physical laws, these are laws that we keep on understanding better and better to more and more improved levels of approximation. So there are really very few laws that one would take as 100% sacrosanct, and some of them of course are the conservation laws. So you can apply conservation of mass, conservation of momentum, conservation of energy, and then set up your physical model or the physical laws that you will ensure is getting followed while using neural networks. So if you look at this type of physical laws, whether it is law of conservation of mass or momentum or energy, you will find that these laws permeate almost all of material processing methods. If you think in terms of doing some kind of a heat treatment experiment, well, when you are doing heat treatment, you are heating the material and getting the mass to flow, but as the mass diffuses from one region to another region, mass actually does get conserved. So using the mass conservation law can have its benefits. Another common example where people have been using physically informed neural networks is where they have to deal with situations that brings in the Navier-Stokes equation. Navier-Stokes equation and fluid dynamics per se, when you are looking at it, it's all about looking at conservation of momentum. Same thing with conservation of energy when you're looking at heat conduction and so on. So when you look at the different types of transport processes in materials, you will find that usually these conservation laws are the ones which underlie all of those processes. And then, of course, why is our fascination with neural networks so much that instead of looking at other physics-informed machine learning programs, we are looking at only the physics-informed neural networks? And that really comes from the fact that how we are using the activation functions with the neural networks, as you have already seen in the earlier lectures of this course, where the idea is you will be using some kind of a highly nonlinear type of activation function. And when you have this combination of nonlinear activation function, you can pretty much take any signal or any curve and then divide that into small units, and you will find that each of those units can be approximated by this highly nonlinear type of activation function. But then when you have this nonlinear activation functions, you essentially the universal approximation of any function, the challenge you will face is you have to pair them up with a pretty large number of neurons and nodes in order to train those functions effectively. And the way you can train something effectively without getting into the overfitting regime with large number of neurons and nodes is only by having a pretty large volume of data. So this is really why working with sparse data becomes so challenging with neural networks. Now, the neural networks that we have been looking at so far are what I would call a black box neural network. Some people may not be very comfortable with calling them black box, but then a lot of people do tend to call them black box. And the reason we are calling them black box is because this entire decision making process in a neural network is actually very, very complex. And so it's extremely difficult in order to get any physical insights from this type of neural networks in an easy manner. So if you look at a typical black box neural network, it is going to compute an output from a set of inputs. So it's just going to give you the number without really telling you anything about physics of the process. This neural network has been trained over a certain finite data set, and essentially if you look at the process of training a neural network, you will realize that this is a technique that does a great job when it is trying to interpolate within the data. So it's great when it comes to interpolation, but it is not really that robust, not necessarily that robust if you are in the extrapolation regime. Now, of course, how well it's going to work or not is definitely going to be a function of whether you are overfitting or underfitting it. But then just be advised that while one can go ahead and use this neural networks where interpolation is needed, they are not that great when it comes to extrapolation. And finally, when you are using a black box type of neural network, because you are not necessarily putting a lot of physical inputs directly, you might be using some features which have been computed using some physical principles, but you are not constraining the neural network per se to follow the laws of physics. So in such a situation, there is no guarantee that the predictions are going to satisfy the conservation laws or the governing partial differential equations of your physics-based model. And this is really where this physics-informed neural network shines. Like the black box neural network, it is also going to compute the output based on the set of inputs, but then the output is such that it is constrained by the laws of physics. So this is one significant difference between your black box neural networks and the physics-informed neural networks. And since these neural networks are basically constrained by the laws of physics, they do a much better job than the black box neural network when it comes to doing extrapolation. In other words, you do not have to fear quite as much that whatever results you are getting out of the PINNs are something which cannot be extrapolated over and outside the data regime on which you have trained the model. And since these are physics-informed paradigms, this is going to reduce the risk of getting some sort of a unphysical output, and you will be more or less confirmed that whatever output you are getting is well aligned with the laws of physics. So this is one of the advantages that you will have in the physics-informed neural network. Now, in addition to this advantages of PINNs, there is of course some caveats. So for example, if you look at PINN, because you are essentially running two things, you are running a black box neural network which is paired with something which allows you to work with the PDEs, the PINNs will turn out to be very heavy when it comes to the computational time. So usually, if you want to really explore the physics, or if you want to create a model which builds in the physics, you have to sacrifice the time efficiency for the physical accuracy. On the other hand, if you are looking at this black box based neural networks, despite being some fairly deep neural networks, they can actually run much faster than your PINNs. So it really depends on what you are trying to do. If you value the physical constraints, then it's better to go ahead with the PINNs. But then if you are not really going after the physical insights and you are more concerned with ensuring that you are getting a fast result, then the black box neural network is what you will typically be working with. The field of physics-informed neural networks came about due to the work of these three researchers, namely Ricci, Perdicaris and Carniadakis. Their paper on using this concept of physics-informed neural network was published in Journal of Computational Physics back in 2019. So it's not been that long, it's just been a little bit more than 6 years that people have actually come up and proposed this concept of PINN. Now the advantage when you are working with PINN is, unlike your black box neural network, you can finally start working with sparse data while at the same time using deep neural networks. And then you can supplement the measured data, which would probably be few in numbers, with the physics-based models, which typically will be coming from the solution of the partial differential equations. And this is one technique by which you can think in terms of getting relatively meaningful results from data sets which otherwise you would consider as incomplete, or models which you would consider as incomplete and improperly trained. So this is really where one sees that this physics-informed neural networks shines. How do these physics-informed neural networks look, and how are they actually going to be different from your traditional black box type of neural networks? So if you look at this figure over here, this is really how a traditional neural network looks. On the left hand side, you basically have your input layer, and then this is a neural network which is 2 layers deep. So these are your hidden layers, and then on the right hand side you have finally got your output layers. Now, when you are working with a neural network like this, the loss function in a very simplified form is going to look like this. You will be summing over all the data that you are using for the training, and then essentially what you are doing is you are simply taking the difference of the observed values and the predicted values, squaring it, and then you do a least square type of minimization. So this is your loss function. This is the traditional type of loss function, and a standard NN is going to try and minimize this in order to get to the optimal values. Once you try and incorporate the physical loss, now what happens is you start writing a new loss function of your own, and then this loss function is going to be a function of the residuals from the partial differential equation, the boundary conditions or the initial conditions loss, and then the data loss when you are comparing it with the measured data. So this is a very standard way in which you think in terms of the loss function as you are moving into the PINNs. You have to compute the value of the partial derivatives. You have to compute the value of the partial derivatives, and then you have to find the residuals there. After that, you have to ensure that the predictions are aligned with the boundary conditions as well as the initial conditions, and you need to look into the data loss. So if you think about it, in a traditional neural network, you might be having your number of epochs along this direction, and then the NN function is going to converge pretty fast like this. Whereas if you use a physics informed neural networks, now again you will be having some convergence coming about, but usually what's going to happen is you may have to do a lot more number of steps, a lot more number of epochs, and then what happens is each time you are doing an epoch, you will be having some points where you will see that there is a significant amount of physical loss. So along this epochs axis, you will be able to figure out a large number of points where you have got the significant loss coming in when you compare this with the physics-based model. So as you try and minimize these losses, the neural networks gets progressively trained better and better. So this is the basic idea of the physics-informed neural networks. Just to illustrate this a little bit further with an example, let's think about our diffusion problem. So according to Fick's laws of diffusion, you will be able to get two different differential equations. The first one talks about the flux, and we say that J is equal to minus D gradient of the concentration, and then the second law is something which relates to the time derivative. So del C by del T equal to D del square C. Therefore, when we talk of problems based on diffusion, these are the partial differential equations that is governing the process. So basically what we will now do is we have to compute the relevant partial derivatives, and then after we are able to compute the partial derivatives, we can calculate the loss functions and then check to the extent that the physics is being violated. What we will do is, anytime the traditional neural network associated with this or the neural network parts of the PINN violates the known physics, there is going to be a penalty associated with it, and essentially it is going to try and minimize the penalty, and in that process train itself in a physics informed way. So that's the general idea. So for instance, if you have the output over here, you can start computing the concentration gradients in x, y and z direction. So that might be the output. In a diffusion problem, your input is going to be the location in your material and a certain snapshot of time. So your input is basically x, y, z and t, and then the output would give you the concentration gradients along each of those directions at that x, y, z point at the snapshot in time t. Now, if you want to compute the derivatives, you have to start looking into Fick's second law, and that is where instead of computing only del x, you have to compute del square del x square. So essentially what happens is, to your standard neural network, now you end up adding a second part, and the second part is really where you are computing the derivatives. The second part is really where you are building in the physics in your system. So we will look into this process a little bit more clearly now. But in order to do that, let us first appreciate how one will implement this physics informed neural networks. So the first thing you have to do, as with any other problem, is you need to define the problem properly. So what that would mean is, if you are working with a partial differential equation, you have to define the domain on which this PD is defined. You need to specify the boundary conditions. You need to specify the initial conditions which is needed in order to solve this particular partial differential equations. Then you start with whatever sparse data you have got and then train the neural network. Having trained your neural network using the sparse data that you have, you will now feed forward the output to the second part of PINN, which is where the physics gets implemented, or rather suggested. So in this second part, you are essentially computing the residuals using the PDs that you have defined, and you are also computing the loss in terms of the boundary conditions and the initial conditions. So once you have calculated the residuals and the loss, you will be able to calculate the total loss. After that, you want to minimize the loss, and when you are minimizing the loss, essentially you are trying to minimize the entire loss function, not just one part or another part. And having minimized the loss, you want to look into performing a convergence test. In other words, what you will really try and see is, when you minimize the losses, is the difference with the previous cycle significantly better or not? If it is not significantly better, then once again you have to iterate. And so when you are iterating, what you have to basically do is update the weight and bias of the neural network as well as the value of x. So this is what happens when you do not have convergence. You go back and you again train your neural network, keeping in mind that the weights and the biases will be informed by an attempt to minimize the loss function, and once again you go over the entire process. Now, when in the process of minimizing the loss function, if you finally achieve convergence, then you will stop and you have your solution. Now you have to understand something though, that even though we are calling it a physics informed neural network and we say that this neural network is being constrained by physics, this is only partially true. Essentially, when you are looking at the loss function contains a lot of the terms from the physics of the process, but it also has an aspect where it is looking at the residuals when the neural network itself is getting trained. So in that sense, we are trying to put a constraint from the laws of physics. We are trying to suggest the model to follow the laws of physics, and that is really the best we can do. You don't really have an exact solution in this case, in the sense that if you try and see whether the momentum was indeed conserved based on the output that the neural network is spitting out, you might not see 100% match. There is always going to be a little bit of small numerical differences. So that is something that you have to keep in mind when you are working with this physics informed neural networks. So the challenging part, therefore, comes over here. So this is where we are incorporating the physics, and when we say that we are incorporating the physics, we have to put in the constraints for the partial differential equations. So let us try and illustrate this a little bit more clearly. Let us take any partial differential equation. So here you can think of this term h as an operator which operates on this function u in order to set up the partial differential equation. Now, supposing the PINN prediction you are getting is being given by this u theta x of t, what next? You have to compute the physics loss term. So the loss term is calculated using this expression over here. The physics related loss is 1 over NC times the summation of this function itself, where you are using the u theta solution that you are having, and of course you are taking the square in order to get the residual. Now this term NC is what we call the number of collocation points, and this is actually very important. These are essentially the points in the domain over which this PD is defined and you have actually done some amount of measurements. So this is going to correspond with the physical measurements that you have done. And then in order to compute these values, like I said, H over here was a differential operator. So there has to be a differentiation which goes on here in order to compute these values, and the differentiation is basically what we call an automatic differentiation. Now as we minimize the loss function, essentially what we are trying to do is we are trying to keep two things in mind. The first thing is we want to have zero loss, or at least as close to zero as possible, at the co-location points. So what this does is it ensures that whatever neural network model you develop is going to match with the measured data values. And then the second thing, of course, is keeping the first condition in mind, you will want to minimize the overall loss. So this is all that we are doing over here. The only new thing that we need to look into is this concept of automatic differentiation. So when we are doing automatic differentiation, we are basically taking two steps. The first step is to break down the function that we are going to differentiate into simple constituent units. So when I say simple units, it could be something like addition, multiplication, or it could be things like taking a logarithm, or maybe some very basic trigonometric functions. The advantage of breaking down the entire expression into the simple unit is that every unit has its own rule of differentiation. And so once you break down your function into simple units, you can start applying the derivative rules. The next step, of course, is to go ahead and apply the chain rule systematically in order to perform the differentiation. So unlike other types of differentiation, whether it is symbolic differentiation where a lot of algebra is involved and then the entire term can sometimes get quite messy, or numerical differentiation which is not exact and it can generate a good amount of noise, automatic differentiation is quite exact and efficient. So this is why automatic differentiation gets used in this physics informed neural network type of approaches. Now there are a large number of libraries that one can use in order to implement this physics informed neural networks where the automatic differentiation is pretty good. Nowadays those libraries could be something like let's say the PyTorch, TensorFlow also has it. In addition to that, a number of researchers are also working with Julia when it comes to implementing physics informed neural networks.
So let us look at this with an example. Let's take a function like y equal to sine of x square and then see how automatic differentiation can be implemented. So one can implement automatic differentiation in either the forward mode or the reverse mode, which is basically what we call as backpropagation. Now as we discussed, we have to take the first steps in terms of decomposing this function into simpler units, and so that is where we will break this original function as y equal to sine of x square into two functions. The first function is u equal to x square and then the second function is y equal to sine of. So when we are looking at it in forward mode, essentially what we do is we store the value of u as x square and we store the value of y as sine of u. On the other hand, the backpropagation becomes useful when there are few outputs and many inputs. Essentially what we will be doing here is we'll be working backwards, and so therefore instead of starting with the initial function, what we see is we find dy by du to be cos u, and then we find du over dx to be 2x, and from there we compute that dy over dx is going to be cos of x square times 2x. So in case of your back propagation, we are working backward. We will be computing the function value from the forward pass, and then we start working backwards. And essentially what we do is we'll be propagating the gradients from the outputs backward towards the input using the chain rule. So in a nutshell, when you are looking at this physics-informed neural network, you need to appreciate that this is giving you a unique perspective, especially if you happen to be an experimentalist. So for instance, if you are doing some really careful experiments, you can make a few number of measurements and you can constrain that those values should always fit with whatever prediction the neural network is giving. So having made the constraint that there are certain collocation points where you have got zero loss, you can then ensure that the physical loss is minimized in order to give predictions which are grounded in physics. So that is the basic idea of physics-informed neural network. Thank you very much for joining with us. Until we meet next time, see you.